Okay, so we have a little bit time left, so let me actually go on and discuss actually why this upwinding scheme is actually not what we actually use in short capturing schemes. So the reason is non-unique solutions. Okay, so let me describe a case where I have two solutions, both satisfying the integral form of the differential equation. So still we have the Burgers equation. W squared over 2 equal to 0. Okay, Burgers equation. And the solution I want you to consider is W0 of x is equal to either 1 or minus 1. Previously, we have the 1 on the left-hand side and the minus 1 on the right-hand side, right? So the left is always crashing into the right by moving at opposing directions. But now let's consider it's 1 actually on the right and the minus 1 on the left. So I have a solution that looks like that. Intuitively, I have a wave on the right that moves towards the right, and the wave on the left actually moves towards the left. So what's going to happen in the middle? What's going to happen in the middle if two paths actually get moving apart from each other? Okay, so I have an answer that it actually gets smooth, right? You expand it, you actually get stretched. The discontinuity gets stretched out to be no longer a discontinuity. That's actually what I would expect too. But if you look at the differential equation, if W is like that, what is the derivative of the flux with respect to x? Well, if the solution is like this, W0 squared over 2 is always equal to half, right? And the derivative is equal to 0. So if you plug that into the differential equation, solution doesn't change. I have a stationary discontinuity constantly being stretched out and get something out of nothing in some sense. Okay? Okay, so this is actually two solutions, right? So one solution is W is equal to W0 forever. So that's kind of the solution. That seems to be the most obvious solution in the mathematical sense. But the physical solution is actually a bit different. So that's one solution, mathematical solution. And there is another solution that also would satisfy the differential equation, and it also looks more physical. Okay, the other solution is how do you describe a discontinuity being stretched out to be no longer a discontinuity? Of course, we still have the 1 or minus 1 moving according to the speed, right? So if x is greater than t, right, because it's moving at the speed of 1, right? And if x is less than minus t because it's moving at a speed of minus 1. So they still are 1 minus 1. There is nothing that can change that. Well, while in the middle, what if x is between minus t and t? How about just a linear function, right? How about x divided by t? Well, basically, I have a solution that is becoming like that, right? Initially, it's infinitely steep, and then it fans out. I would say this also satisfies the differential equation, because if you look at any particular height, the movement of the height is proportional to the height, right? If you plug this into the differential equation, you see it's perfectly satisfied. All right, so there are multiple solutions. And how would you argue that one solution is more physical than the other? In real life, which one is the one that happens? Huh? The second one? Why?
Well, I guess the entropy title, but something's going to change, something's going to move, it's not going to stay in the same place.
Oh, okay. So actually, my question is ill-posed because when I say physically what happens, and I didn't say what kind of physics this equation describes, right? So you have to actually, if you want to say physically what happens, you have to actually link it to the physics. So for example, the Burgers equation is actually a pretty good description of how a sonic boom propagates from like near a supersonic airplane to the ground. And if I want to describe the Burgers equation for that physical phenomenon, then I can argue the second solution is the right solution. Because Burgers equation, just like describing the wave crashing into each other, it's actually a model. It's not exactly the real physics. And there are something missing in the model, just like the assumption that breaks when the wave breaks. The assumption in the shock propagation or the sonic boom propagation is that there is actually a very, very small right-hand side that is something like this. Viscosity, right? The viscosity is actually very, very small because I mean, just the order of magnitude is like the viscosity of air, which is like 10 to the minus 5, divided by the speed of sound, which is like 10 to the 2, right? So you get like on the order of 10 to the minus 7 viscosity here. And that's negligible. I mean, 7 order of magnitude separation is negligible in most cases, except for when you have a discontinuity, right? So what is the viscous? I mean, if you remember, we did Fourier series, right? When we have a Fourier series, the viscous term is going to dissipate the higher frequencies according to the frequency squared. So for most frequencies, you actually see for smooth solutions, this term doesn't matter if mu is on the order 10 to the minus 7. But if you have a discontinuity, the discontinuity actually contains all frequencies, even very high ones. And if you try to dissipate the very high frequencies, it will immediately make this, and remember, this is a parabolic term, right? A parabolic term affects everything immediately, right? So the domain of dependence of a parabolic equation is like the everything after t equal to 0. So you have something that would still almost look like a discontinuity, but if you zoom in, you'll find out it's actually a smooth solution. And once you have a smooth solution, it's basically something like this, but like the steep is it's extremely steep, and the argument I have over here no longer works, right? The flux instead of being a constant half, it's going to be half except of a very sharp dimple all the way to 0, right? And this makes it impossible for me to have this solution. This solution is actually non-physical if the equation describes something with an infinitesimal viscosity. All right, so now this actually non-unique solution makes the upwinding scheme actually makes it don't work in some cases, and we can show you in the next lecture. And also the recipe for fixing that is called trying to solve what's called the Riemann problem, right? It's actually trying to exactly solve what would happen in the physical sense when the discontinuity is evolving for infinitesimal amount of time, okay? And that provides the correct solution for giving the flux evaluation. All right, I'll see you on Wednesday.